Good afternoon, everyone. I welcome you all again in this faculty development program on progress on 2D materials. So this session 2, will be presided over by Dr. Syed Arshad Hussain. Dr. Hussain is an associate professor of physics at Tripura University. His major fields of interest are thin film and nanoscience, organoclay hybrid, breadth, biosensor, biomimetic surfaces, organic memory, etc. He was a postdoctoral fellow at KU Leuven, Belgium during 2007 to 2008 and visited 11 countries for academic and research purpose. He has undertaken research grants amounting of rupees 4.3 crores funded by DST, CSIR, DAE, UGC, etc. Dr. Hussain has published more than 135 research papers in international journals, written 3 books and edited 4 books and 1 patent in his credit. He has attended more than 60 seminars or conferences and delivered 24 invited lectures in India and abroad. He is working as editorial board member of Applied Clay Science, Helion, recent present in nanotechnology, micro and nanosystem, nanoscience, and nanotechnology Asia. Dr. Hussain has already guided 9 PhD scholars and 3 MPhil students. At present, several students are working under his supervision. He has visited 11 countries and attended several scientific conferences in India and abroad. He has organized 21 scientific events as convener or organizing secretary, including 3 international conferences. Dr. Hussain is a member of various professional bodies like APS, MRSI, ISCA, IAPT, PANE, ANS, AGU, etc. He earned several recognitions in professional area. Few of them are Jagadish Chandra Bose Award 2008-2009, given by TSCHT, Government of Tripura, Young Scientist Research Award by DAE and DST by Government of India, Visiting Scientist by KU Leuven, Belgium, Best Paper Award in 96th ISCA Felicitation by Asiatic Society of Bangladesh, etc. This year, Tripura University felicitates Dr. Hussain for his academic achievements with medal and certificate. So, the session will be given by Dr. Hussain. Dr. Hussain, all yours.
Good afternoon. So, am I audible?
Yes, sir. You're audible.
So, I welcome you all once again in this second session. So, let me share my presentation and I will switch off the video. Okay, then it will be easier. So, can you see my screen?
Yeah, it is absolutely fine. You can go on.
Okay. So, today I will speak on two-dimensional clay material. It's a natural nanomaterial, and how this material can be used as a host material to manipulate the properties of organic materials for various applications. So the mainly I will share informations to highlight this area, and I will share some of our findings also, but not going too much technical details. If somebody is interested, then we can discuss later. Okay, so this is some kind of informative kind of thing. So already Professor Pal has discussed some basic things about 2D nanomaterials. Mainly in case of 2D nanomaterials, one dimensions of the material has to be lower cut down of the order of nanodimensions. So there are a lot of examples already. Professor Pal has said. So when we cut one dimension of the material and make it two-dimensional, then the material, so many changes in the properties occur, mainly due to high surface area, surface functionalization. One can functionalize the surface using other system. You are uh, 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 one-dimensional quantization also occurred because you are confining your one dimension to the nanoorder. Then you have surface charge. There may be surface defects. Material may be flexible. So many issues are there. And due to these, several properties changes with respect to its bulk counterpart. Properties like thermal, structural, chemical, mechanical, optical, electrical, and so many. Accordingly, there may be lot of applications in optoelectronic devices like LEDs, sensors, then optoelectronic devices, energy sectors, biomedical applications, quantum device, storing device. So many applications are promising, mainly due to this change in properties with respect to its bulk counterparts. Okay, so today mainly I will discuss on two-dimensional clay nanostructure. Mainly initially I shall try to give an overview and or introduction about clay material, then why clay is interested to the material scientist. Then I shall discuss something how one can prepare this organoclay system in two dimension, and then some examples. So we all know that soil is alive with living organisms and it supports life systems. Without soil, it's difficult to sustain the life on this earth. So as a whole, one can say that soil is a complete self-sustaining ecosystem. Basically, soil consists of sand, silt, clay, organic matter, and this kind of things. Therefore, one can say that clay is a subset of soil family. Clay exhibits plasticity when mixed with water and becomes hard, firm, rigid once drying. And due to these, there are a lot of applications of clay. And basically, they are used in construction industry, crockery, pot making, medical, cosmetics. But here, we are interested in preparing organoclase systems mainly to manipulate the property of the organic material, which may be suitable for optoelectronic applications, including sensing. Now, what is clay mineral? Clay mineral represent an important group of layered inorganic solid material. They swell in aqueous dispersion into single sheet with thickness of the order of nanometer and diameter, say micrometer to fraction of micrometer. It has colloidal size, high cation exchange capacities, large surface area, adsorptive properties, then viscosity, transparency, all this kind of property makes it very interesting. But the main interesting property of clay is intercalation. That is, it is possible to incorporate both polar as well as non-polar material within the interlamellar space of the clay layer, and this property of the clay gives the opportunity or makes the clay as the ideal host material to incorporate organic material within the system. Now, basically, clay minerals are layered systems, and each layer of clay is composed of combinations of two different sheets. One is a repeat unit of tetrahedra of Si4 plus, silica tetrahedra. Repeat units, it's a sheet kind of thing. I will show later. And then another sheet, octahedra of alumina, magnesium, or iron oxides. Okay, so combination of these two sheets, and different kind of cation or anion in between the sheets make different types of clay. And based on the combinations or arrangement of these sheets, there are different kinds of clay. Say TO, that means one tetrahedra sheet and then one octahedra. It's a clay layer, and then it will repeat to form the crystal. 2:1 means one tetrahedra of silica, then octahedra, then again tetrahedra. Then it will repeat. In this way, you will see the clay crystals. Now, basic building blocks of clay mineral, that means clay sheets, are silica tetrahedrons, SiO4, and alumina octahedrons. So, schematically here it is shown silica tetrahedrons. So, you can see here two repeat unit. In this way, it forms continuous repeat unit and form a sheet of tetrahedra. Similarly, this is alumina octahedrons. You can see this is the unit of the aluminium or magnesium octahedron. Then this is repeat units form the sheet, octahedra sheet. So ions, molecules, they form sheet, either octahedra or tetrahedra. Then sheet upon sheet, it forms layer, and layer upon layer, it forms crystal. Okay, so layering of silica and alumina sheets together results in different types of clay, and also based on the composition within the interlayer space. So here again in this cartoon it is shown. You can see this is silica tetrahedron, this is the sheet, this is the alumina octahedron, this is the sheet, and this is joined together to form the layer. And again silica, so this is a TOT, so this is a clay layer, TOT type. Okay, so layer upon layer it will form crystal. So some example, kaolinite group. So this is 1:1 TO type. Then mica, this is also one kind of clay. This is 2:1 TOT. Then you have other different types of clay. So this is another example. It's a leponite clay, and this is a TOT type. That means tetrahedra sheet, then octahedra sheet, then again tetrahedron sheet. So this is a unit of clay layer, and these are the ions or cations in between the layer. So this is the chemical structure. So this is the leponite, and this is circular in shape, and diameter is of the order of 20 to 50 nanometer, and you see the thickness is 1 to 2 nanometers. So this is a leponite clay. Similarly, another example, this is hectorite. This is again TOT type. There is tetrahedra, octahedra, then again tetrahedra, but interlayer space cations or ions are different. So accordingly, you can see the chemical formula or composition is different, and also the shape. You can see this is rod-like shape. Okay. So interesting thing is that it's a layer structure, and based on the layering as well as type of the cations or ions in between the layers, one can have different nanomaterials with different shape. And we know that at nano dimension, properties are shape dependent. That means one can play with the properties by choosing different types of clay. So this is interesting. Okay. Now, one of the interesting property of clay is that if you, this is swelling of clay. If you put the clay in solvents like say water, it will swell. And if it is a clay crystal, by following proper methods, you can have single sheet, either octahedra or tetrahedra. Okay, so it's possible. So this is swelling of clay mineral. Okay. Then, okay. So this swelling is mainly, there are two reasons. One is hydration of exchangeable cation, and another is the difference in ion concentration. Sorry, in between the clay sheets and the outside the layer. These two difference, there is some kind of osmotic exchange of ions occurred, and swelling of clay occurred, and the sheets or layer get separated from one to another, and it results ultimately to the single sheet of the order of fraction of nanometer. Then intercalation, you can incorporate the other material within the clay sheets or within the layer, or you can attach your organic material or polymeric material or suitable material even on the surface of the sheet also. Okay, so you can attach them in the edge also. So this kind of things is known as intercalation. Okay, so this is just schematically shown. You can see here the organic material or your foreign materials is incorporated on the edge of the clay crystal. Then you can see in between the clay sheets. Here also you can see that it's possible to incorporate polymer around the clay crystal. You can put your polymer in between the layer or in between the sheets also. So different types of hybrid structure you can have, just playing with the environment, playing with the controlling the system. So this is another example. You can see you can physically link your polymer or other material with the clay sheet, you can see, or layer, and mainly this attachment is due to electrostatic interaction, then ionic bonding, hydrophilic interaction, hydrophobic interaction, dipole-dipole interactions are prominent here. Similarly, chemically also you can link your material on the clay, and mainly this interaction is covalent in nature. So these are some schematic showing how you can have the structure. Another interesting property of clay is cation exchange capacity. Cation exchange capacity is the sum of exchangeable cations that your clay can absorb. That means if you expose your clay in a medium containing some cations, then the ability how much it can incorporate these cations within the clay systems. And there are several factors, strength of cation adsorption or cation exchange capacity depends, there is a series, lyotropic series. So if this type of cations are there in your system, you can see there is a high probability that Ba+2 will incorporate in the system faster. And adsorption also depends on charge density, that is charge per volume or per gram unit of your clay system, and also size of the ions also. So this cation exchange capacity of your systems allow the clay an ideal host to incorporate other material or other functionalized material through cation exchange reaction. And main exchangeable cations are within the clay system. It exists, say, Ca+2, magnesium+2, sodium, potassium. So when you expose your clay, these kind of cations from the clay exchange with the environment, and your foreign particle will incorporate within the system. And this cation exchange capacity is expressed in mega equivalent per gram. So here again, one example, you can see the material is incorporated through intercalation in between the clay sheet or say surface. You can say incorporate even micellar kind of thing. So it's possible through a cation exchange reaction. So this is just an idea that it's possible different type of organization within the clay system. Now, if you compare your clay with other two-dimensional material, say graphene or MOS2 or other material, because graphene is one of the most, talked about two-dimensional material. But the main issue of this material is about toxicity, because in nanomaterial, most of the material are toxic. So whenever you are, say, proposing any applications, you have to, specifically if it is health related or human related, you have to take care of its toxicity. Okay, but main interest in clay, you can see one layer of the order of say 1 nanometer. Okay, so but main interest is of the that this clay is a natural material and this is eco-friendly, layered structure, and very easy to incorporate organic material within the clay system. So these are the advantage of clay with respect to the other two-dimensional nanomaterials. If you look into this graph, you see number of publications. You see this is taken from the Web of Science. You can see number of publications here increasing. You can see even citation also increasing with almost steep rise. So that means people are paying attention towards clay, okay, or doing research for using clay for future applications. Okay, so here some examples, say in biomedical applications, one can find applications in almost all areas, like say bone, then wound healing, tissue adhesive, protein therapeutics, then drug delivery, 3D bioprintings. So many applications are coming up using clay or clay organic systems. Only thing, you have to choose proper combinations of your material so that you can have the clay organic hybrid with desired properties. Again, one example, you see nanoclay stimulate bone regenerations. I have taken this. This is not my work. I have taken this just to show you that clay has applications in diverse field. You can see they suggested that the bone regeneration accelerate if clay is used in the system. Similarly, you can see nanoclay loaded hydrogels are used for delivery of stem cells for cartilage regenerations. And researchers very optimistic good results are. Another thing, 3D bioprinting. So in 3D bioprinting, are using 3D printer where ink is sometimes using living cells, and they are preparing different type of organs so that it can be transplanted within the human body. You can see in the YouTube also there are a lot of nice video are there, and that in near future time when different organs like kidney, liver, heart may be printed directly within the body using 3D. So researchers say that nanoclay based hybrid material is very suitable to print living organic organs, human organs. Then another thing, there are in internet, I have seen there are a lot of works are going on synthesis of artificial RBC, and scientists say that if combinations of suitable material with clay help blood vessel formations, and in near future maybe artificial blood might come into reality where clay can play an important role. So in our research group, we are mainly in organo-hybrid systems. We assembled them onto thin films. Our main aim is to explore new organoclay hybrid nanomaterials for different applications like sensing, biosensing, catalysis, electronics, etc. So we on say study of organizations and how the organizations relates with the change in property. So this is our main aim, and we also applied these systems to manipulate the fluorescence transfer and also designed some kind of optical sensors also. And recently, we are designing some kind of clay-based supramolecular assembly to apply them in colorimetric sensor naked eye. It's something like litmus paper kind of thing. Just observing color change, even you in naked eye, one can have idea about the sensing. So I will show some example. So these are some related works from our lab on optical sensor using clay-based system. Then we designed several hybrid nanostructures, which shows several applications like sensing, biosensing, catalysis, etc. So these are the related papers. These are some other papers, mainly for organic memory. Okay, so now why we are interested in organoclay system? Why not only organic material? Mainly, the planarity of the pi conjugated system of the confined organic molecule is increased when you incorporate them within the clay system. As a result, the pi conjugation length of your material extends, and also the fluorescence quantum yield of the organic material get enhanced. Why? Because when you incorporate your organic material within the clay system, it suppresses the vibrational motion of the confined molecule. Due to these two properties or two change in the material, one can have interesting optoelectronic behavior of the system or of the organic material incorporate within the clay system. Another thing, one can play with the clay layer gallery height. That means one can play with the thickness or gap between the sheets within the clay layer by simultaneous drying and wetting. And in this way, one can play with the organization of the material and hence the optoelectronic behavior of the material. Therefore, organic molecules confined in clay organic hybrid system exhibits unique optoelectronic behavior that are not observed in the pure form or pure organic system. Here, I just try to show you that if we prepare, say, thin films of your of organoclay system, then there may be two different types of organization. One is, say, this is clay, this black one in the substrate. Then this red one, your organic material, may organize on the surface of the clay or on the substrate. At the same time, it is also possible to put this organic material in between the clay layer also. So this kind of organization is possible. And if one can play with this organization, one can play with the property of the organic material confined within the system. So this is interesting. So here I show you see just by say controlling the clay environment, one can control the organizations and one can have you see this is a polar molecule, dipolar molecule, but the moment by organizing the molecule, controlling the clay structure, you can play with the dipole moments. You see here moments is not equal to 0, but here it is 0. Here again not equal to 0, but here this is 0. Here again not equal to 0. This is just an idea that one can play with the organizations within the clay system. How you prepare your organoclay hybrid films? We take help of different techniques because these thin films are of the order of nano to micro dimensions, and you need special care, special technique to prepare it. You cannot prepare with your hand. It's not possible. So sophisticated techniques like we use Langmuir project technique, self-standing films, spin coating technique, layer by layer self-assemble technique. In my say last FDP, I discussed details about Langmuir project technique, how this can be used to prepare two-dimensional material. So here I will not go details on the techniques, but so this is the instruments for preparing LB films using Langmuir project technique, and this is a instrument attached with fluorescence imaging microscopy. So on the during film formation, you can observe the happenings. Similarly, this is attached with Brewster angle microscopy, so you can have idea how your materials is going to be organized during film formation. So these instruments, we have this in my lab. So in LV technique, it's very simple. You prepare your molecule on the water surface first, you spread, then you compress so that they come closer, then you deposit. Just simply, if you dip a spoon on the cream formed on the hot milk and take out, you see cream attached on the spoon. So here also same thing happen. But of course, here you have to be very careful because you cannot see it. So everything is computer controlled. So ideally, you can have a layer of molecules having one molecule thick using this technique. Okay. So how we organize clay in this film? So in LB system, what we do in the LB trough, we prepare clay dispersions of single sheet of clay. Then we put suitable cation on the surface. Through cation exchange reaction as well as electrostatic interactions, this clay attached with the floating amphiphile like this. Then we compress with the barrier so that form compact film. Then we take out the substrate in this way. So the film, organoclase film, is transferred on the substrate. During the film formation, one can have, idea how these interactions or film is forming, because this is a time-dependent process. Your clay is on the surface, then you are spreading amphiphile here. So with time, it is coming on the surface like this. So there is a system. This is in situ infrared reflection absorption spectroscopy. So if you monitor using this instrument, the organizations of your films on the surface with time, you can have idea. Here you see the plot of SiO vibration. We already shown that silica tetrahedron is there in the clay. So if you measure using IRRS the SiO vibration intensity, you see that with time, you see here it increases. That means number of clay sheets coming on the surface is increasing with time, and after some times it flatten. This is for one type of clay, and this is for another type of clay. You see here also, but of course reaction is different. Okay, so it's flattened because there may be situation is like that, no free cation in the surface is available to incorporate further clay sheets from the surface. Similarly, using AFM also, during the film formation, what we did, we transfer the film, say after 5 minutes, and after 30 minutes, you can see the difference in concentration of the clay sheets. So this is a time-dependent process, and you can monitor the reaction kinetics using IRRS, using AFM. There are other techniques also. Then we prepare self-standing films of organoclay systems. It's very easy. We prepare dispersion of clay. Then we put the organic material we want to prepare, the incorporate in the clay system in the this clay, and we put it on magnetic stirrer, then ultrasonication. Then we use this suction system. There is a membrane. This is a cellular membrane kind of thing. Say it's nanometer order pore size. Then we put this mixture here and we suck using a vacuum pump. And within the membrane, the film form. Then we transfer the film from the membrane to the substrate we want to deposit for characterizations or for applications. So we peel off the membrane and we have these films on the substrate. Or if you can have self-standing film also, you can simply peel off the film from the membrane also. It's possible. Then spin coating is very common. It depends on the rotations of the substrate. So you put your dispersion or mixture here. So you rotate. So it's form a something like a layer. But here control is less compared to other techniques. But you can prepare. Okay. Then sometimes we use layer by layer technique also. So here, say we use oppositely charged functionalized substrates on the, say, desired material, maybe some cationic material, then this is negatively charged. If this is anionic material, then this is positively charged. Then we dip, we wait sometimes, then we take out. So this interaction again time dependent. One can have study by changing the deposition time. One can have idea about the reaction also. Okay, then we take out, wash out, then we put in the clay. Then clay adsorb, you can see, and one can repeat this process to prepare multi-layer also. So this is also a simple technique, but we have an instruments, computer controlled dip coater to use to prepare this. But simply one can work with using simply beaker and substrate, so it's very easy. So this is AFM image of some organoclay LB films. You can see this is saponite. You see thickness less than 2 nanometer, then leponite, again of the order of 2 nanometer, Wyoming, then hectorite. But interesting thing is that you see the shape, size is different. That means you can prepare different types of hybrids using different types of clay. So here I show you one example. Say this is pyridinium derivative. Okay, so we say prepare hybrid self-standing films using a saponite clay and this pyridinium. Okay, and it's a self-standing film, so using this technique. So here, once we prepare the film, we recorded the image using simple camera, digital camera. Okay, so you see in the first column, these different images are for different concentration of clay. Okay, so you see that this is the just simply film is prepared. This is the image. Here also, this first column is as prepared. Then we put some solvent. Here we use DMSO in the clay. Then again we observe no color change. Second row, you see, it's exactly similar to the first row. But when this swollen film is exposed to UV, you see the color is changed. You see, and then if you just light using a UV torch, you can, using your naked eye, you can see the color change. Okay. And these are, so I am not discussing these things. So we mainly, this thing happens because when these molecules incorporate on the clay layer, depending on the gap of the sheets within the layer, initially in dry condition, molecule organized in one molecule layer. This is because we apply XRD to measure the gallery height. And in dry system, this is of the order of 0.48. Okay. And when swollen, we have observed that the thickness increases to 0.93. That means there is a possibility that molecule stack together, they form pi-pi stacking. Okay. And then again, we studied using this fluorescence spectroscopy and also lifetime. Fluorescence, you see, in swollen, there is longer wavelength band, broad band. This is mainly nature of excimer. Excimer means special organization of molecule where one excited state molecule stack with a ground state molecule. Okay, so you don't need to follow all these things, technical things. Okay, so this is a stack of one ground state molecule, one excited state molecule. So how we confirm? Initially through this fluorescence spectra, then lifetime, because excimer has longer lifetime compared to the monomer, and we measure the lifetime here, this broadband, and here also monomer, and we see that lifetime increases 18 times. So we conclude that in swelling there is a formation of excimer or stacking within the system. Excimer is an excited state phenomena, so in normal light you cannot see the color change. But when you excite with UV or wavelength close to its absorption, you can see the color change. Okay, so you see this is the simple prepared film, then swollen under UV. Then interesting thing, if it is washed with water and again dry, you see original color come up, and it is reversible. Different cycle, you can dry, you can swell, so you can switch between these two color. Okay, so here schematically you see two molecule stacked together in swelling conditions, in drying one molecule. Okay, so we propose this may be used for secret writing. This is, you see, simple your film as prepared. Then what we did, say using a hearing bud, we dip in the DMSO and written something, say TU here. Then we observe with normal light, you see this below image, nothing is seen. But when we light this film, this written film using UV, you can see this thing. Okay, so again you wash it, you can go back to the original color. So this can be used as a secret writing. This is another example of this is an indolil derivative and saponite clay mixture. Initially, you see this is colorless. When it is dried, it is red, and then swollen, this is yellow. An interesting thing is that it is observed that color switches between this red to yellow. This is for different concentrations we show. Okay, and you see the color switches between red and yellow for different many times. So we dry it, then we swell, then again wash out, then again dry in this way. And here main thing is when heated, then oxidation occur, it becomes red, but when dry, molecule will become flattened, pi conjugation length enhances. When it's swollen, molecule get twisted, conjugation disturbed, so color change occur. So we confirm this through XRD and spectroscopic study. So interesting thing is that one can have color switching, which can be used for designing colorimetric sensor or optical memory. Then another example using clay PDA, polydiacetylene mixed system. This is a self-stranding film of, you see in membrane. It's a clay PDA film on cellulose membrane. This is the PDA. This is the DA, diacetyl monomer. Through UV, one can polymerize it. And of course, there are some requirements. This monomer should close enough, say 4.7 to 5.2 Armstrong. Then their stacking angle should be of the order like this. And then if you expose to UV, they polymerize. Okay, and they show prominent color, blue, and this is, one can observe it through naked eye. Then again, through further UV or temperature or other stimuli, it's possible to change the organization of or orientation within the polymer. That means this rotation of CC bond within this polymer, so that this film become red. An interesting thing is that this transformation is totally observable through naked eye. So this is very interesting. Okay, so this is very common molecule in internet also you can see. So what? Okay, so this is the spectral feature of this molecule. This is in blue phase, then this is in red phase. Another interesting thing, in blue phase, this material show no fluorescence. You see here, this is one in before UV, that means black one is monomer form. After polymerization in blue phase, this red line, you see no fluorescence. But when red phases, you see prominent fluorescence. Okay, so this is very interesting spectroscopic signature. So we prepare a TCDA. This is an polydiacetylene, then clay, then one imidazole. This is an organic material synthesized by my friend in chemistry department, and we make an hybrid system, thin films, and we demonstrated several sensors like volatile organic compound, gasoline adulteration, pollution level of car exhaust, alcohol sensor, this kind of things we have designed. Okay, so again, this is simple. We prepare using this method, this film here. Then upon UV, we change the color, we transform this. That means we did the polymerization, so blue color appear. This is blue phase of the PDA. Then we made a, this is a simple design system. We designed this simple, say, a container containing material to be sensed, and in the lid we put this film in blue phase, and with time you see the color changes. Okay, so we put VOC gasoline here, or sometimes we put this film on the silencer of the car also, while sensing the car exhaust pollution level in the car exhaust. Okay, so you see the response or color change from blue to red for 12 different volatile organic compounds. Okay, so this is for clay PDA system, and this is clay PDA with imidazole. Here you see the response is better, but of course concentration of different VOC show different response, and also time also different. So one can optimize this whole thing. Okay, then you see the extent of color change is also different. So by observing color change, you can have idea that yes, this volatile compound is there or gasoline is there, but for quantifications it's difficult by observing the color change. Then what we did, using MATLAB software, we designed a small program, and we extract the RGB color from pixel of the image of these films before color change, that is exposure to the analyte, and after the color change. Okay, and we defined a normalized signal intensity, which is the red divided by blue before after exposure, that is after conversion to the red, and then this R0 by B0, this is before exposure. And from this, if this is increasing, that means conversion towards red is higher. So we see that this shows linear behavior with concentration, with time. Okay, so you see these are the plot. You see it shows almost linear. So from here you can quantify that yes, this amount, this concentration of VOC is there, this concentration of gasoline is there, this much of adulteration is there. It's possible. So this is our system. We expose it on simple gasoline. You can see PDA clay, then PDA clay imidazole. You see here response is better, but gasoline is possible to have idea that yes, gasoline is there. Okay. Then what we did in normal in our region, what we observe is that sometimes people mix kerosene with petrol because kerosene is cheaper. Okay, so we try to try our sensor, okay, how it can respond if it's adulterated with kerosene. So we mix kerosene with the petrol and we expose our sensor to this adulterated gasoline, and you see the color change. You see normalized signal intensity changes, decreases linearly with increase in kerosene within the gasoline. That means it can give you idea, yes, kerosene is there in the gasoline. Okay. Similarly, we try to have idea about the exhaust level, pollution level in the car exhaust. So what we did, initially we prepared the film using suitable organic material and clay. Then we put on the here. No, then we expose it under UV, converted into blue. Then this blue film we put it here. You see, with time, it started responding in 5 seconds. Then you see in 10 seconds, 15 seconds, 30 seconds, it totally converted to red. Okay. Then we extracted the RGB value from there and try to compare with the present pollution level in the car exhaust. How we did it? We tested the car pollution level in the standard, pollution level measuring system, and we calculated the presence of CO2, CO, HC, O2, etc. in the exhaust. Then we compared with our measurement system, and we have seen that the presence of CO2, CO, HC, etc. if increases, then the color change also occurred linearly with the presence of this material. So somehow it can have idea, it can give idea about the pollution level of the car exhaust. But of course, a lot of experiments, lot of optimization is required. Okay. Then another example is a Clay PDS system for alcohol sensor. You see, this is a simple image taken by a digital camera in blue phase. Then this is, this film is put in front of the mouth of a drunk person and he gave puff. You see the color changes. And this is after some times also it responded. Okay. So color change occurred. Similarly, you can see this is before exposure to the drunk person. You see after drunk person, you see the structure also changes. Okay. So normally alcohol sensor available in the market, these are mainly resistivity or conductivity based. So you need a battery, you need an ammeter to measure the current, then calibration system. But in our case, this is simply a litmus paper kind of thing. Simply you put it in front of the drunk person, you see the color change like litmus paper and have idea whether drunk or not. And you can calibrate using normalized signal intensity to have the concentration of the alcohol consumption. Then again, some example, we use this clay material to see how it affects the fluorescence resonance energy transfer. These are the related papers. So fluorescence resonance energy transfer is an electrodynamic phenomena, but of course it's non-radiative and it's an excited state energy transfer. Here you see you need two molecules, two fluorophore. One is donor, one is acceptor. You excite your donor molecule, it will go to the excited state. It will come to the ground state through non-radiative transition, and it gives energy to the acceptor. You see, and acceptor go to excited state, and it will come back to the ground state through releasing a photon. That means it will show radiations. Okay, so this is a non-radiative excited state energy transfer, mainly due to long-range dipole-dipole interactions of your donor acceptor. Okay. So there are several factors to this energy transfer to occur. Mainly, your donor molecule should be highly fluorescent with very high quantum yield. Your donor acceptor should come very close, 1 to 10 nanometer. That means it's a distance dependent phenomenon. So if the distance changes, the extent of energy transfer changes. So this gives the idea that FRET can be used to have idea about the molecular level interactions, molecular environment. And also there should be sufficient overlap between the donor emission and acceptor absorption, you see. And relative molecular orientation in the mixture, this is also important. So all these factors affects the extent of energy transfer. How you identify that energy transfer occurs? So you see this through just measuring fluorescence spectra. You see this is your red is the fluorescence of your donor. Okay, this is B is the fluorescence of your acceptor. Why this is less? Because you are exciting your donor or acceptor or the mixture with the absorption maximum of your donor, and with that wavelength or with this energy, your acceptor is absorbing very less. So this is very less. But in this condition, if this is a mixture, you see the acceptor fluorescence is very high, although you are exciting with absorption maximum of your donor. This is because donor accepts the energy, it converts to the acceptor, then acceptor radiates, and energy you see here increase in fluorescence. You can have idea using lifetime measurement also. If you measure the lifetime of the donor, then lifetime of the donor in presence of the acceptor, you see the lifetime in the excited state decreases in presence of acceptor. This is because it transfers its energy to the acceptor. So this is the diagnosis purpose. Okay. So how FRET can be used as a sensor? Because we know that distance between donor acceptor, relative orientation of the molecule, then transition dipoles, spectral overlap play crucial role to the extent of energy transfer. If presence of any external agent within the donor acceptor systems affects these factors, your energy transfer efficiency also changes. So indirect way or opposite way, by observing the change in energy transfer efficiency, you can have idea that yes, external agent is there. Simple, you are throwing a ball to one of your friend. If there is no obstruction in between you and your friend, you can simply pass it to him. But if you throw and if it do not reach in to your friend, that means there is something in between you and your friend. So here also same thing. Okay, so this is a very simple system. One can have design different kind of sensor. So to do that, first thing is that you have to identify suitable molecules where energy transfer occur. So we identify two molecules, one is thiazine and di and one rhodamine. And we observe that in pure system, that is when we mix these two molecule, there is no energy transfer. You see, this is red one is for acceptor, blue is for donor, but this is mixture. You see, when we mix, even acceptor fluorescence density decreases instead of increasing, although there is sufficient overlap. But when we mix clay in the system, you see energy transfer increases. And also when we incorporate them in thin films, then also energy transfer occurs. But in presence of clay, energy transfer efficiency enhances from 64.2% to 97%. And this is because you see in clay, the distance between molecules decreases from 13.4 to 8.36 Armstrong. There are some theory. You can calculate the distance between the molecule, the orientation, efficiency, etc. So in between, in the clay system, distance changes, and also you see the orientation, it also changes. Accordingly, efficiency changes. Similarly, again, we designed another system. This is acrylfluorine and rhodamine, where energy transfer occurred from acrylfluorine to rhodamine. You see, in absence of clay, the energy transfer efficiency was 11%, but in clay, this is 78.17%. So almost 7-8 times higher. Why? This is because you see in absence of Clay, distance is say 8.07 nanometer, efficiency also 11.37 nanometer. But when we incorporate this energy donor acceptor in the Clay, they are absorbed in the Clay surface through cation exchange reactions, and you see distance becomes closer. So energy transfer efficiency increases. So here Clay play major role towards increasing the energy transfer efficiency. And using this system, we have designed several sensors, say hard water sensor. In hard water, we know very well, based on the salt concentrations of say Ca ions, Mg+2, Ca+2, etc. We define there are standard definitions. Soft water, moderately hard water, very hard water, etc. Concentration is like that. Okay, this is standard. So what we did, we measured energy transfer between these two systems in presence of different concentration of these ions. And you see the energy transfer also affected due to the presence of these systems. Okay. So this is because in presence of ions, you see what we did. First, we incorporated the material on the clay. Then we measured the energy transfer efficiency. Then in the second system, what we did, first we incorporate ions, Mg+2, Ca+2, etc. on the clay surface. So they occupy on the surface of the clay layer through cation exchange reactions. Then we expose this system on our acceptor donor system. So automatically distance between these two donor acceptor increases because already your calcium, etc. ions are there in the clay systems. So energy transfer decreases. So we try to calibrate this decrease in energy transfer efficiency with concentration of the ions. So you see this is the change of efficiency with the ion concentrations. And from there we plotted this one like that. If energy transfer efficiency is 13.5% or less, then we say that this is very hard water. If the efficiency is 13.5 to 48.2%, then moderately hard. If higher than this is soft. We also designed several other sensors like arsenic sensor, ion sensor, DNA sensor, cholesterol sensor, pH sensor using clay organic material systems. So I am not going details in these things. So this mainly my idea is to inform you that, to share you that it's possible to design two-dimensional organoclay systems with different kind of functionality. If you are interested, then you can read the papers. It's there in the website also. Then we did another type of experiment. This is we try to study the influence of clay on second harmonic generation. You know, second harmonic generation. This is a nonlinear optical effect. This is a one can say that branch of optics that describes the behavior of light in nonlinear media, where polarization density responds or changes non-linearly with the electric field of the light. Okay, although this polarization density show linear change in homogeneous or isotropic medium. Okay, so if your medium is non-linear, this thing happens. There are several phenomena like second harmonic generation, Kerr effect, some frequency generation, two-photon absorption. These all are nonlinear effects. Okay, so second harmonic generations, in second harmonic generation, two photons with same frequency interact with each other within the nonlinear material, and they combine to generate a new photon having frequency double than the initial frequency. Okay, that means if you are say interacting with two photon in the nonlinear medium having frequency omega 1, then you will generate a photon having frequency twice omega 2. This is second harmonic generation. Some frequencies in generation, if you interact two photon having two different frequency, omega 1, omega 2, and if you allow them to interact within the nonlinear medium and generate another new photon having frequency omega 1 plus omega 2. This is some frequency generation. So these are some kind of example of nonlinear optical applications. There are a lot of applications in, say, optical signal processing, say, optical computer, ultrafast switching, then generation of pulse laser, sensor, and many more. Say one example, if you want to generate, say, laser with 532 nanometer wavelength, then it's easy. This is commercially available. What you can say, 1064 nanometer source, you pass through a nonlinear medium, and they will interact and generate your photon having wavelength half. That means frequency double. So this is one commercial application of second harmonic generations. So what we did, we and for second harmonic generation SHG, the material should be non-centrosymmetric in nature. If there is symmetry, then there is no second harmonic generation. Okay, so in LB technique, we can organize material in a suitable way so that even if there is symmetry in the molecule, we organize the material in such a way that as a whole, the whole structure is non-centrosymmetric. Then we can have second harmonic generation. Okay, so you can see here, this is an arrangement. This is a symmetric molecule, but structure is non-centrosymmetric because this is J aggregation, head to tail arrangement in the LV system. Single layer. Okay, so we prepare using a Cation dye. This is without, this too is without clay, this is with clay. So we characterize using spectroscopy. Then you see, without clay, we see that the intensity of the organization or specific aggregation required for nonlinear optical effect changes if there is no clay. But if there is clay, you see this is stable. Then you see SHG signal. This black one is for freshly prepared in absence of clay. Then after 7 days, you see the intensity go down. But when we design the system using clay, you see even after 7 days, you see change in intensity is very less. So clay play an important role to enhance the mechanical stability of the SHG active thin films. This is another example. You see, with clay, SHG signal intensity increases, but without clay, it's less. So, clay play an important role towards organization of the material as well as stabilizations to favor nonlinear optical activity or second harmonic generation. Okay, so I am almost at the end of the my discussions. So we can say that clay materials are very promising for preparing organoclay hybrid supramolecular structures, and one can play with the property of the incorporated materials within the clay systems to have different functionality like colorimetric switching, optical memory, energy transfer, sensing, J aggregation, second harmonic generation, and so many. So we can say that organoclay hybrid films are very promising for future technological applications, and main advantage of the system is this is natural nanomaterials, eco-friendly, because the main issue of the nano systems, that is hazardous in nature, it is totally eco-friendly, non-hazardous. So this is the main advantage. Okay, so I acknowledge my students and co-workers, then funding from DST, DAE, CSIR for all this research. This is my collaborators. So I would like to thank you all for your patience. Thank you very much.
Thank you, Dr. Hussain. So now participants are requested to put their questions in the chat box if you have any. So as I can see, one question is there from Dr. Swati Mehra. Sir, you mentioned nano clay used in regeneration of bones. Is it used in knee replacement? And can it be widely used for all kind of bones and joints generation?
First of all, I would like to say that this biomedical application is not my work. I collected it from internet. Okay, and I have seen just to show that the clay material have diverse applications. I showed it. I am doing mainly optoelectronics applications. At the later part, I shared all these are from my lab. But in the internet or the papers, I have seen that it stimulate the regeneration of bones, and I am sure that it's possible to prepare material suitable for knee replacement and other bones also for joint, etc. It might be possible because now there are in market some materials which can replace bones. Okay, so clay interest is it's eco-friendly, natural, non-hazardous. So people are trying to incorporate using clay also. It's might be possible. Can all types no, no. Yeah, in LB tech, you see there are several techniques for preparing clay thin films. Okay, so normally clay is water insoluble. They also don't float in the surface. They form dispersion, and uh, due to swelling property of clay, you can prepare single sheet, fraction of nanometer thick sheet, either octahedra or tetrahedra, or single layer, okay, in the surface through swelling. In LB technique, ideally one need floating material to prepare the film, floating material. Okay, so what in LB, what we do, you spread your material on the surface. It's like something like, some water plants are there which float on the surface. So you spread there, then you compress with barrier so that they come closer to each other. You prepare a compact film, then you try. So here what we did, since we are interested in organoclase system, so we prepare the dispersion, put on the LB machine, there is a trough, then we spread the suitable material on the surface. It's floating amplified, and we allow some time. So through cation exchange reaction, because clay surface, it's they have negatively charged, they go cation exchange reactions. So through electrostatic interaction as well as cation exchange reactions, when they come in touch with the floating molecule, they get attached. And this is a time dependent process. I showed you it's possible to have idea. So in this way, you can incorporate, if your material and clay pairing is in a proper combinations, you can incorporate all type of materials. But another thing, in soil, there is a lot of mixture. Clay are it's a multi-component system. So one has to have pure single type of clay, because in LB system you are dealing with molecular level. So your material should be very pure to have good film with good property. So ideally it's possible. Then how do one vote for the purity of the clay? Clay should be having a variety of content. Yes, you see, chemical people or soil scientists, they do it. I, as a physicist, we are interested in physical property of the material, not synthesis. So there are lot of research on now artificially also one can synthesize clay. In sigmoid also you can purchase from sigmoid or other chemical company. But there are scientists who can, there are some chemical procedure, they can isolate single clay component. It's possible. And I have also collaborated in Leuven, KU Leuven. They are purifying it, and in my work, all are natural clay. It is not, synthetic. So they isolated it and they have given us. It's possible. A small, please do post this group created by you also. To post this, acha. In this Google Meet, we need to open call message every time. Acha. What is the LOD, detection limit of ethanol sensor? Okay, so
Sir, I think it is limit of quantification, LOQ.
LOQ, acha. Limit of quantification. I told you, by observing, you see, by observing color change, it's really difficult to quantifications. So what we proposed, we take the photograph of the film color change, then we extracted the RGB value and we plotted the normalized intensity, and from there we have seen that it's normal, it's linearly changes, and I think it's 0.02, it's there. It's different for different VOC, different component. Okay, so lowest composition we have, I think it's 0.008% volume ratio. It can sense at the lowest level. Okay, but of course it depends on different components. Then, sir, where can characterization techniques be availed at low cost for faculties and new researchers, as we all are interested to do research, but resources and financial assistance is less in private organizations? Oh, yes. So now you see, now there is a system. This is AICTE, and Government of India form a network with all institutes which have costly equipments, and Mumbai IIT, they are managing this. There is a website, AICTE, you can go there, you search, say in Tripura, in West Bengal, you can find in West Bengal how many institutes they have SEM, how many institutes they have AFM, how many institutes they have NMR facility like this, and there all the description is there, how you use them. Okay, who is responsible, where to mail, what is the cost, everything is there. This is one part. From my end, you can go through my website also, and I have some facility. We have some facilities. Say we have FSM, we have NMR, we have AFM, we have this all spectrophotometer, UV, fluorescence, FTIR, we have film preparation techniques. So we are giving access most of the people if they are interested, but of course in an optimized way, because we don't have dedicated operator. Mainly our scholar operates this kind of machines, so it's availability of these slots, availability of the time, so we try to provide the facility. This is one part, but through government level you search the AICTE, you can have details there. Oh, how to synthesize nanoclay thin films? Is there any technique? I showed you. You can use LB technique. You can use spin coating. You can use layer by layer technique. You can use self-standing technique. There are so many techniques to prepare your organoclay thin films. Okay, so there are so many techniques are there. What is the response time, recovery time, selectivity, and sensitivity of the sensor? It's different for different material. For example, in car exhaust, we have seen that in I think it's in 3 seconds I showed you it's responded, but in even less time also it might be possible, but we did it manually. We put it there, we use some words, so in this way, so it's responded in color changing in 3 seconds. Okay, but it depends on different and light, different material. For example, it's alcohol, its time is different, then car is different, petrol is different. Yes, but exact value is given there in the paper, you can read there. Okay, selectivity, sensitivity also it's there. Sensitivity, selectivity we optimize through normalize intensity analysis. So for exact value, I told you the procedure. For exact value, you can check my paper. It's there in my website also. Okay. Oh, my email ID is there in the university website, or I have personal website is also there. So you can search with my name, you can find. Okay. You can write email. As long as possible, we shall try to help. Okay. We collaborate. No problem.
So as I
Yeah.
can see,
Yeah, yes. Can nanoclay thin film be? Yes. There are a lot of works. I am not doing this work. They are mainly for purifying water. They try to absorb, remove different hazardous dyes, or sometimes insecticides also from systems. It's possible because they are layered material. They incorporate the material through cation exchange reaction as well as intercalation. So it's possible. There are a lot of works is there. Okay, but I am not doing this kind of things. My interest mainly to prepare organonuclear system for optoelectronic applications.
so if anyone have any more question, you can please ask, or you can directly contact to Dr. Hussain to his email ID. He will be happy to directly reply to you.
सर सही बात बोले
So I think Dr. Hussain, all of the questions you have covered, and no more questions are there. So shall we conclude the session here?
Yes.
Okay. So thank you, Dr. Hussain, for your wonderful lecture. So in this way, the first day of this FDP program, we are concluding here. So today, so tomorrow, we will have our session from 10:30.
ఫిగర్ చూసి అందులో ఏ బర్డ్ ఉంటుంది ఆ నెక్స్ట్ లో బర్డ్ నేమ్ రాయాలి
So tomorrow we have our first session from 10:30. All the participants are requested to join by 10:15. So positively join by 10:15. Tomorrow we have 3 sessions: session 3, session 4, and session 5. So thank you for joining here. So we'll meet tomorrow. Thank you.